Hello friends, in this video we are going to discuss about the Bond model of semiconductor. At first, for the Bond model of semiconductor, we have to know some different topics. Likewise, first we have to understand what is wave particle duality. Next, we need to know the elastic wave. And the third one that we need to know is the why do we need the elastic wave and wave particle duality. And the fourth part that we need to know to understand the Bond model of semiconductor is the bridge between the wave world and the particle world. And the fifth thing that we need to know to understand the Bond model of semiconductor is what is the value of wavelength associated with a particle having energy 1 electron volt. So these fifth things, that is, these are the 5 things that we should know before going to the Bond model of the semiconductor. So let us first discuss about the wave particle duality. So according to the wave particle duality, it states that any energy propagates in the form of stream of particles. That is, suppose there is a wave which is propagating from point A to point B in this fashion. Now, according to the wave particle duality, if a energy, that is a wave, propagates from point A to point B, it means that this wave can be thought as some particles, that is the stream of particles. These are also propagating from point A to point B. That means any wave which are traveling from one point to another point, they can be thought as some stream of particles are propagating from that one point to another point. So we can say that when an energy or a wave propagates in the form of stream of particles. Similarly, when a matter propagates, then it is propagating in the form of traveling waves. So if we want to discuss this statement, it means that if I have a matter like this, and if it has a mass m, then suppose this material or matter is at position A. By some force, it has came to another position B like this. Here the matter mass m is also the mass m. Now we can see that this matter is propagating from point A to point B. According to the wave-particle duality, we can think this phenomena like this way, that there is a wave associated with this matter which is propagating from point A to point B. That means any wave in this world can be thought as stream of particles. Similarly, any matter in this world can be thought as traveling wave. This is wave-particle duality, which states that every energy or wave propagates in the form of stream of particles, or every matter propagates in the form of traveling waves. Now, to understand this phenomena inside the semiconductors, let us see how many traveling waves that can be produced inside the semiconductors, and what are the corresponding particles with that traveling wave. For that, let us take a chart. The chart will look like this. Suppose I am making a chart like this. In the first column or in the first row, I can say that I am writing particle stream. That is the name of the particle stream. In the second row, I am writing the traveling wave. That is the corresponding traveling wave of the particle stream. Now, every traveling wave, when travels, then there are some parameters inside the traveling wave which will change with respect to position and time. So in the third column, I can write those parameters which vary with respect to time and distance of the traveling wave. And the fourth column, I am writing the name of the equation of the traveling wave. It means that the fourth column, this fourth row, denotes the name of the equation which will denote the traveling wave equation. Now these are the four rows that will give the table. Now let us see how many particles that can be found inside the semiconductors. The first particle that is found inside the semiconductor is photon. The second particle that is found inside a semiconductor is electron. The third particle that is found inside a semiconductor is phonon. So these are the three particles, major particles, that are found inside the semiconductors. So in the first row of the particle stream, I have written the three particles. Now in the second row, let us see what are the traveling waves that are associated with these particles. So for the photon particles, the traveling wave that is associated is the electromagnetic wave. So we can say that this electromagnetic wave is the wave nature of these photon particles. Similarly, the wave nature that is associated with an electron is called the de Broglie wave. Similarly, for the phonon particle, the traveling wave that is associated is the elastic wave. So we can see that every particle, that is photon, electron and phonon, are associated with different traveling wave. For photon, there is electromagnetic wave. For electron is associated with de Broglie wave. So phonon associated with elastic wave. Now let us see what are the parameters that will vary for the each traveling waves with respect to time and distance. For electromagnetic wave, the parameters that will vary with respect to time and distance is the electric field and the magnetic field. So these are the two parameters that will vary with respect to time and distance inside the electromagnetic wave. Similarly, for the de Broglie wave, which is a wave associated with the electron, so in a de Broglie wave, the parameter that will vary with respect to time and distance is the probability. So the probability parameter will vary with respect to time and distance in the de Broglie wave. Similarly, for the elastic wave, the atomic displacement parameter will vary with respect to time and distance inside the elastic wave. Now, let us see what are the equation or what is the name of the wave equation that is associated with the electromagnetic wave. That means, what will be the name of the equation that denote the electromagnetic wave, that is called as the Maxwell equation. So the Maxwell equation describe the electromagnetic wave. Similarly, the de Broglie wave is described by the Schrodinger equation. But for the elastic wave, there is no such a single equation which can describe a elastic wave. There are so many equations. There are so many equations that will describe the elastic wave. There is not a single equation like the de Broglie wave or electromagnetic wave, but for the elastic wave, there are so many equations that we found in the real world that will describe the elastic wave. So these are the particles and the traveling wave associated with the particle inside the semiconductor. So from the wave particle duality, we can conclude that if we have a matter, suppose these are the matter or particles that are moving from one point to another point, then there will always be a wave associated with this matter which is traveling with respect to time and position with the particles. Similarly, when a wave is moving or traveling from one point to another point, suppose point A to point B, then we can think that, or we can say that a matter is associated, or the particles are associated with this wave which are also moving from point A to point B. So this is the conclusion of wave particle duality, which gives that every matter in this world can be think as a traveling wave, and every traveling wave can be think as a particle. Now, the second part that we need to know to understand the bond model of the semiconductor is the elastic wave. So, what are elastic waves? There are so many examples in the real world that will give the elastic wave, like the traveling wave that we found in the guitar string. That is also a elastic wave. Similarly, if we throw a stone in the pond, then a ripple wave will be generated on the water of the pond. That ripple wave in the pond is also an example of elastic wave. So, in this elastic wave, it is a traveling wave. So, from the wave particle duality, we have seen that this elastic wave can be think as or can be thought as the atomic displacement of the particles. That is, in elastic wave, the atomic displacement will change its value with respect to time and position inside the wave. And another example is that of the elastic wave is the sound wave. The sounds that we hear through our ears is also an elastic wave. And this sound wave is an important example of the elastic wave. Now, we know that an elastic wave can be thought as a stream of particles, and the name of the particle is phonon. That means we can explain the elastic wave as a stream of phonon particles. And this word phonon comes from the another word. The origin of the word phonon is the phono. This phono means sound. So, in this topic, we can see that an elastic wave is a traveling wave, and this traveling wave can be thought as a stream of particles, and the particle name is phonon. Now, let us discuss the third part that should be understood to get into the energy bond model of semiconductor, that is the importance of elastic wave and the wave particle duality. So before understanding the importance, let us discuss about the wave world and the particle world. So far, from the wave particle duality, we came to know that every particle in this world can be thought as traveling wave. Similarly, every traveling wave can be thought as stream of particles. So we can say that there are two types of world in the physical environment. The first world is the wave world and the second world is the particle world. Both of these worlds are analogous to each other. So, since the total physical system can be described into two worlds, first one is the wave world and the second one is the particle world, that means there must be a connection between these two worlds because both the wave world and the particle world are analogous to each other. So let us see how we can bridge these two worlds with each other. So as we know that the energy, that is the capital E, is denoted by H into nu, where this E is the energy and this nu is the frequency of the wave, and this is the energy of the particle. Similarly, we also knew that there is another equation, P equals to H by lambda. This P is the momentum of the particle and this lambda is the wavelength associated with the wave. Now, if we look into these two equations, we can see that the left hand side of the equation is related to the particle world because energy and momentum are the parameters for particles. Similarly, the right hand side of the equation, that is the frequency and the wavelength, this is related to the wave world, and this H is the Planck's constant. So these two equations, that is E equals to H nu and P equals to H by lambda, is giving a bridge between the two world, particle world and the wave world. So in this way we can put a bridge between the particle world and the wave world, where the E and the P are the energy and the momentum of the particle, and mu and lambda are the frequency and the wavelength of the wave. Now let us see the fourth part that should be understood to understand the Bond model of semiconductor is how much wavelength will be associated with minimum energy. Let us see what will be the wavelength associated with the minimum energy particle. So for this, we know that the minimum energy that is possible for an electronics device is 1 electron volt. So 1 electron volt is the minimum energy that we can denote for the electron device. So This 1 electron volt can be converted into a joule unit, that is 1.6 into 10 to the power minus 19 joule. So 1.6 into 10 to the power minus 19 joule is the minimum energy possible inside a semiconductor. Now let us consider, for this case, that we are talking about electromagnetic wave. That means, for this discussion, we are considering that our traveling wave is electromagnetic wave. So the wavelength that will be associated with this electromagnetic wave we need to find. So our objective is that what is the wavelength, that is lambda, associated with this electromagnetic wave having energy of 1 electron volt. For that case, let us take the equation P equals to h by lambda, where P is the momentum and lambda is the wavelength of the electromagnetic wave. We also know that the energy relation, that is E equals to h into nu, where E is the energy of the particle and nu is the frequency of the electromagnetic wave, and this h is the Planck's constant of the particle. Now, from these two equations, we can say that if we put P by E, then it will look as h by lambda divided by h into nu. Now, after simplifying this equation, I will get 1 by lambda into nu. So, this is an equation of the ratio of P to E. It will come as 1 by lambda into mu. Now, if we consider the velocity of the wave as small v, so we can write it as velocity of the wave is nothing but the multiplication of the frequency and the lambda. So if we replace this v value in this equation, so it will come out as 1 by v. So we can say P by E is equals to 1 by v, where v is the velocity of the wave. Next, what we can do, that we know that lambda is equals to h by p, because p equals to h by lambda. So from this equation, if we put the value of p from this equation, if we find the value of p will be e by v. So if we put the value, it will look as v divided by e. So lambda is equals to h into v divided by e. So from this equation, we can find that lambda is equals to h into v divided by e, where v is the velocity of the wave, e is the energy of the particle, and lambda is the wavelength of the wave, and h is the Planck's constant. Now we can see that this equation holds for the wave, because this wavelength is a parameter of the wave. Now if we substitute the value of h, and the value of h is given by 6.626 into 10 to the power minus 34 joule per second. If we substitute this value in this equation, then we will get that lambda is equals to 6.626 into 10 to the power minus 34 joule per second into velocity divided by energy. Now, let us consider that the electromagnetic wave that we have considered previously for this discussion, the velocity of the electromagnetic wave is always the speed of light, that is 3 into 10 to the power 8 meter per second. And we are finding the wavelength lambda for 1 electron volt energy, minimum energy. So if we replace these two value in this equation, we will get that lambda is equals to 6.626 into 10 to the power minus 34 into velocity 3 into 10 to the power 8 divided by energy 1 electron volt. After calculating the lambda, we will get the value of 1.24 into 10 to the power minus 6 meter, or we can say 1.24 micrometer. So from this discussion we can conclude that if a particle has 1 electron volt of energy, then the wavelength of the wave that will be associated with that particle will be 1.24 micrometer. This is an important conclusion that will be used inside the Bond model of semiconductor. Now, let us discuss what will be the advantage of using this information, that is the wave particle duality and the elastic wave. So what is the importance of wave particle duality and the elastic wave? For that, let us take a semiconductor like this. For that purpose, let us take a semiconductor bar. This is a semiconductor bar, and in this semiconductor bar, let us assume that light is incidenting on this particle in this way. So this is the light that is incidenting on the particle. Now we know that the light is nothing but the electromagnetic wave. So this situation, we can say that it is a situation where the electromagnetic wave is interacting with semiconductor. That means it is an interaction of electromagnetic wave with the semiconductors. Now, this electromagnetic wave is in the wave nature. So we can say that wave will be interacting with the matter, that is semiconductor. So in this type of situation where the waves are interacting with the matter, for that case, the wave particle duality and the elastic wave will come into the picture. How? Let us see that. For that case, for understanding this, we know that according to the wave particle duality, the electromagnetic wave can be thought as it is a stream of photon particles. This comes from the wave particle duality, because wave particle duality depicts that every wave in this world can be thought as stream of particles. For electromagnetic wave, the particle name is photons. So we say that the electromagnetic wave is nothing but the stream of photons. And every photons will have energy of E equals to h nu, where nu is the frequency of the electromagnetic wave. Now we can say that these photon particles will collide with the semiconductor atom. So we can write that photons will collide with the atoms of semiconductor. So due to the wave particle duality, we have converted wave matter interaction to particle matter interaction, and the name of the particle here is photons because the wave name is electromagnetic wave. So it has become a simple problem of collision. Now this collision problem can be treated with respect to energy momentum conservation point of view. So we can write that the collision problem right now can be treated with respect to energy conservation law. Hence, using the wave particle duality, we can see that the electromagnetic wave, when interacts with a semiconductor, it has converted into a stream of particles interacting with the semiconductors. In this way, a complex situation can be converted into a simple situation of collision problem using the wave particle duality. So this is the advantage of wave particle duality, which will convert the complex situation for the case of semiconductor into a simple situation. Let us take another example of how the wave particle duality will make a complex situation a very simple one. For the case of semiconductor is that, let us consider for that a semiconductor. So this is a semiconductor bar or material. Now this semiconductor bar is at T equals to 0K. That is, the temperature of the semiconductor bar is 0 Kelvin. So when the temperature of this semiconductor bar is 0 Kelvin, now we want to increase this temperature beyond 0 Kelvin, that is T will be greater than 0 Kelvin. So let us see what will happen if we increase the temperature of the semiconductor. So for that, when the temperature of a semiconductor is increased beyond 0 Kelvin, we know that inside the semiconductor there will be so many atoms. So these are the atoms of the semiconductor. Now, when the temperature of the semiconductor is increased, these atoms will start vibrating. All the atoms will start vibrating. So if the atoms start vibrating, we can say that atoms will be in agitation. Agitation means vibration. So when we increase the temperature of a semiconductor, the atoms inside the semiconductor will get agitated. So we have seen that when the temperature is increased beyond the 0 Kelvin, this atom of the semiconductor will start vibrating in this fashion. So vibrating atom means there will be some atomic displacement with respect to time and distance. And this vibrating atom will produce, according to the wave particle duality, a traveling wave called the elastic wave, because during the vibration of the atom there will be atomic displacement that will vary with respect to time and distance, and this vibrating atom will produce elastic wave. So we can write the atoms will give rise traveling wave. So what will be the name of the traveling wave? The name of the traveling wave will be the elastic wave, because here the atomic displacement is changing with respect to time and distance. So every atom inside the semiconductor will give rise elastic wave. So we can say that at T greater than 0 Kelvin, semiconductor has agitated atoms and they will produce elastic wave. Now these elastic waves that are created due to the atomic vibration, these elastic waves will now propagate inside the semiconductor through the atoms. Now, according to the wave particle duality, we can say that these elastic waves are nothing but the stream of particles. Stream of particles. We have already discussed that any elastic wave can be thought as stream of particles, and that particles is nothing but the phonon particles. So we can say that due to the increment of temperature of semiconductor, a new particle has been developed inside the semiconductor due to the vibration of the atoms, and that particle is the phonon particles. Now these phonon particles will interact with the atoms of the semiconductor, and there will be some phenomena. So we can say now there will be the interaction of phonon and electron of the semiconductor. So in this way we can say that the increment of the temperature phenomena of a semiconductor has converted into a interaction of phonon electron inside the semiconductor, and this has only happened due to the wave particle duality concept and elastic wave concept. So this is the advantage of using the wave particle duality for the case of semiconductor. So this is all about the topics we should need to understand the Bond model of semiconductors. Thank you.